second edition of our LIFELIKE computing systems workshop. I said this is the second edition of the LIFELIKE workshop. It is, but it is the ninth edition in our evolution of the workshop series on autonomously learning and optimizing systems, shortly SAOS. And I will spend some words more on that. So first of all, I want to say hello and welcome to this workshop. And I think that all of my co-organizers are here, and I would also ask them to say some words about them in the next few minutes. Let me just start because I'm talking anyway. My name is Anthony Stein. I'm from the University of Hohenheim here in Germany, where I have a tenure-track professorship of artificial intelligence and agricultural engineering. And yeah, I pass the ball further to Sven then.
Yeah, hello, welcome everybody from my side. My name is Sven Tomforder. I'm from Christian Albrechts University in Kiel in northern Germany, and I have a professorship in intelligent systems there. Okay, next one is Jean.
Hello everyone, I'm Jean Botev. I'm from the University of Luxembourg in Luxembourg. I'm with the Collaborative and Social Technical Systems group there. I'm a senior research scientist. And yeah, I was about to introduce myself because the next talk is mine. So I just pass on to Pete.
Thanks, Jean. Hello, everyone. So my name is Peter Lewis, call me Pete. I was at Aston University in the UK for several years. Some of you may know me from there. I've moved very recently to Canada, to Ontario Tech University, where I hold a Canada Research Chair in Trustworthy Artificial Intelligence. It's great to be here. Thanks.
Cool, thank you. So I already said something about this evolution of our SAOS workshop series. And as I said, this is the 9th edition in our series on autonomously learning and optimizing systems. But if you check the history of this workshop, you will also find the name self-optimization in organic and autonomic computing systems, which was the name it initially started. The entire workshop series is rooted in the German Organic Computing Research Priority Program, which went from 2005 to 2011. It was a quite big research program in Germany from the German Research Association. And we started with our first edition in Prague, actually, but not online, but in person. We moved to several cities, among them Lübeck, Porto, Nuremberg in Germany, Vienna, and Braunschweig, as we call it in Germany at least. I think in English it's Braunschweig, but I'm not sure. Then we started thinking about, well, maybe we could shift a little bit the focus of our workshop, and we did it. And it was then called Intelligent Systems Workshop in 2019, and it was hosted in Copenhagen. And since then, all the editions were hosted by the Architecture of Computing Science conference. And then we started thinking again, and decided to try to move to another conference venue. And we were successful. We get the permission to host our workshop here at ALife for the first time last year in 2020. And it was also, of course, due to the COVID pandemic, a virtual event. And unfortunately, it is still this year a virtual event, and hopefully it is the last time where we have a pure online workshop. Maybe next year we are in the situation that we can at least have a hybrid one. It would be great, at least I think you will all agree on that. So since 2020, we call our workshop the LIFELIKE Computing Systems Workshop. And why we do this is on that slide, where I want to briefly say some words about our motivation. We aim at understanding and building computing systems able to act robustly in highly dynamic environments. And these systems should also be able to adapt flexibly to continuing change, which is due to the deployment of our computing systems in the real world, right? And therefore, we pursue to render these systems lifelike by means of endowing them with self-X. Maybe you are more familiar with the term self-star properties, such as self-organization, self-improvement, but also self-explainability and self-awareness. But this is not an exhaustive list, of course. And the first talk within this year's edition presents our new vision paper, a paper from the organizers of this workshop, where we postulate a first selection of some qualities of life, as we call them. And these qualities of life we deem very, very crucial for being implemented, or at least leveraged by future computing systems, which we think of are lifelike computing systems. So let's have a quick look on the workshop agenda for today. We are in the middle of our welcome note, and afterward we start with our vision paper on lifelike computing systems to introduce you more to our notion, which is in our heads, and yeah, want to convey this notion also to you all there. This talk is given by my co-organizer Jean, who introduced himself a little bit before, and afterwards we have a very exciting keynote by Dr. Felipe Campello from Aston University in UK, and he will give a talk on sharks, zombies, and volleyball, which sounds quite interesting, and on supernatural computation mechanisms or heuristics that gone wild in the past. Afterward, we start in the first contributed paper session. Yeah, to be honest, our lifelike computing systems is also contributed. Then we have a talk by Helena Steker from the University of Augsburg. She will tell us something about analyzing meta-heuristic components. Oh, I see there, I forgot to delete paper PDF, which is from the website, but this is maybe a good point to make some advertisement of our workshop webpage, where we also published all the works already. So they are online, all the papers are online, you can download them from our workshop website. Yeah, thanks exactly for the link. He posted it in the chat. Okay, and then we have a short lunch break of half an hour, and we then start again in our contributed paper sessions number 2, which is then chaired by my colleague Sven Tom Forde. And we have a interesting talk by Christopher Landauer from California and Topsy House Consulting. He will talk about what I want in a computational partner. The talk afterwards is given by Michael Haider, again from the University of Augsburg in Germany, and he will introduce us to the concept of learning classifier systems and how they can be employed in self-explaining socio-technical systems. We then have our last contributed talk for this edition, which is a concept for self-explanation of macro-level behavior and lifelike computing systems, which is then given by Sven Tom Forde and from the Kiel University in Germany. And afterward, we have time for a quite short but good closing session chaired by Pete, where we have an open discussion and then have a short summary and a goodbye for you. So that's mostly all I want to say, but I did forget the publication policy of our workshop to make it a little bit more interesting for you for further contributions maybe. So first of all, I want to shout out a big thanks to our great program committee, which allowed us to have at least 3 peer reviews per paper that has been submitted to our workshop. All the papers are online at our workshop page. You find a link here and in the chat, and also in the Slack channel. And our publication policy is as follows. We plan to publish a mini volume with an own ISSN over the ceurws@ws.org service. This is a German service where we can submit mini proceedings for maybe workshops here. And then these mini proceedings or mini volumes are regularly indexed by DBLP, Scholar, Google, and Scopus, for example. And they are all open access, and the authors also keep their copyrights. This is one of the unique things here of this service. And in addition, we invite all the accepted papers to a planned special issue on lifelike computing systems in a renowned journal, which is to be defined by the end of this year or the beginning of the next year. So all the accepted papers will get an invitation to extend the work and submit it to a journal there. Okay, so then that's all I wanted to say. And I would like to pass the ball now to my colleague Jean Botev from the University of Luxembourg, who will give the first talk of this workshop on our vision of lifelike computing systems. Jean, audience is yours.
All right, thank you, Anthony. Let me try and share my screen. So you should be seeing something right now. Okay.
We see your background so far.
Exactly. That's a good start. And now you should be seeing the slides.
Yes, we do great.
All right. Okay, yeah. So thanks, Tony, for the introduction. Welcome again to all the attendees here at the LIFELIKE Computing Systems Workshop. Tony kind of halfway introduced what this is about. So I would basically, skip maybe that part. But in this vision paper, basically me and my colleagues, we take the first steps outlining what constitute lifelike computing systems, why such systems are worth striving for in the first place, and what we need in order to pave the road for them, right? So my name, as you heard, is Jean Botev, and I'm a founding member of the Collaborative and Social Technical Systems Research Group and head of the VR lab at the University of Luxembourg. So let's just get going then and start with a very foundational and fundamental question, really. Why lifelike computing systems? All right. So first of all, I would like to stress that the term lifelike computing systems is not intended to replace or separate itself from previous initiatives. Right? In a large number of cases and specific settings, there are already technologies and research efforts that strongly lean towards what we deem are lifelike computing systems. What we do, though, is we take a different kind of view, if you like. Our focus is rather on a holistic view of the different properties and how they can be developed as an ensemble and the fruitful combination of those. So how can we learn from the study of life and living systems so that we can develop new practical and engineered technological systems that possess lifelike qualities or properties, and also to identify when such complex features are of particular value. So what are lifelike computing systems really? As also Tony mentioned in his introduction, in his foundational work, we try and identify an initial set of characteristics or qualities, actually it's 5 of them, of life that we consider absolutely essential for lifelike computing systems. And I would like to start with the very first, or let's say foundational quality of any living organism and natural system, and that is their continuing evolution. And we not only think of typical evolutionary computation techniques here, but explicitly emphasize open-ended evolution, all right? So we need complex mechanisms to steer systems toward continual, adaptive, flexible, and creative behavior that also Tony mentioned as one of our goals with the kind of self-start properties. For instance, basing the fitness also on stimuli that are beyond numerical utility values. And I mean, for instance, here you could think of novelty detection and positive reinforcement of behaviors, which might be one possibility. But more broadly, fitness is not static or fixed and may often arise endogenously within the environment and the people and others with which a system is interacting, right? So we see this in a broader context and take this kind of holistic or meta perspective. So open-ended evolution is obviously a fundamental trait, but then one of the most distinguishing qualities between living and non-living systems is intelligence, right? So as is already the case for the notion of life, there's again no universally accepted consensus on what exactly defines natural intelligence, right? So, however, typical capabilities would include like rational thinking, problem solving, reasoning, both on certain or, which is more interesting, even uncertain knowledge, the acquisition of competence, skill, and knowledge via learning, the use of intuition and other mental heuristics, self-awareness, various forms of reflection, but also emotional thinking and creativity, right? So this is all part of this intelligence complex. And once more, there's no universally accepted consensus here. Depends really on the discipline, on what the focus is or which kind of characteristics they pick in that sense. And beyond thinking of intelligence on an individual scale, for lifelike computing systems, collective intelligence is particularly important, right? So in natural living systems, on an individual basis, you find often that not every organism can be considered particularly intelligent, right? However, in nature, we have often like remarkable capabilities when these kind of simple constituents or non-intelligent constituents act collectively. They can do that either in smaller groups or in larger swarms. And oftentimes this kind of self-organization governs in decentralized systems and results in emergent phenomena that sometimes are understood as intelligence, or if you like, intelligence of a superorganism, right? And if we strive for evolving computing systems that are comprised of intelligent system components, we must not only bear in mind that the potentially undesired side effects this has, but also develop ways to quantify these and measure these, detect, control, maybe by enforcing positive and then simultaneously also dampening adverse emergent effects. So emergence is an important quality here in lifelike computing systems. And another striking property really of living systems is their resilience to disturbing events or disturbances and gradually changing conditions, right? This occurs at multiple levels. So often depends also on the severity then. So we have the level of the individual organism, population level, and further even whole ecosystems, right? And indeed, resilience can and also needs to be viewed on different hierarchical and also temporal scales, right? And the essence of this fourth quality is that for lifelike computing systems, mechanisms will be needed that minimize this brittleness of the technical systems so that we can tackle the inherent complexity of the world they're embedded in, right? And we cannot do this by only insulating them, right? So it's actually trying to minimize that brittleness, yet keeping them open, because again, they're embedded in a larger context with complex interactions, right? And I mean, indeed, social technical settings generate dynamic and often unforeseen and compound environmental, societal, and legal conditions, really. So we cannot really insulate this. And this again plays then directly into the fifth of the characteristics of lifelike computing systems that I would like to mention here, which is social awareness, right? And the ability to establish social behavior, that's to empathize and reason socially about others, to create and also follow social norms, is really a fundamental quality of human societies, but also animal societies. And such societies face challenges that increasingly occur also in technical systems, right? And in lifelike computing systems, we need mechanisms to interact with unknown participants in open systems, right? To recognize interdependencies, also mutual influences, to develop and also comply to norms that govern autonomous individual behavior, and also to explain the inner reasoning of the system, both to human and other stakeholders. And other stakeholders could also include software, right? So every kind of constituent within the system. And as I mentioned at the beginning, this is not an exhaustive list, but a set of what we consider really pivotal characteristics, which are often studied separately in various subdisciplines. However, in lifelike computing systems, they form a compound and are really important for this holistic view that we are taking. So where are we now? There are various approaches and initiatives that focus on the different system qualities and characteristics that I mentioned before. And I would like to show a couple of them now to basically contextualize the research with the concept of lifelike computing systems. And for instance, in multi-agent systems, we have agents that take their decisions based on predefined goals and then are able to interact with each other. And for lifelike computing systems, as we envision them, especially the existing technology here for interaction schemes and also protocols that would provide valuable starting points, right, from MAS, like multi-agent systems, and mostly for the qualities of emergence and social awareness, right? So each of these kind of initiatives or approaches that I mentioned now kind of looks at specific aspects or characteristics that I mentioned before, and obviously as such contributes also to this larger vision. So then we have autonomic computing, or AC. And the idea of autonomic computing is essentially that you have an autonomic backbone structure in your system, which relieves the system designer from specifying all possibly occurring situations and configurations within the design process. Because again, in open systems, it's highly unlikely that you can foresee any given configuration or any given occurrence. So instead, the system itself then takes over the responsibility to find appropriate reactions to the changes it perceives in the environmental conditions. And although this is still limited to dedicated control problems, autonomic computing or the contributions of autonomic computing related to particularly self-adaptation have clearly helped us equip also technical systems with, in particular, I would say, more intelligence and resilience, just to map back to those characteristics that we think of. So again, this is a kind of a different sub-research domain that contributes to this overall vision. Then we have proactive computing, which builds on the notion that this human-in-the-loop computing has its limits due to the sheer number of computing devices or interconnected computing devices. And proactive computing is mostly a vision and strongly focuses on hardware challenges, but the motivation still holds also for lifelike computing systems, right? Because we also think that the scale in itself and the number of devices that are part of such lifelike computing systems exceed what can be controlled by traditional measures, right? So we can really draw inspiration from this proactive computing vision for nearly all qualities that I mentioned earlier. Similarly, to master this kind of ever-growing complexity of technical systems, the Organic Computing or C initiative takes inspiration from natural and biological systems, basically transferring formalizations of self-star or self-X properties, as Tony said, to engineered technological systems, which is very important because lifelike computing systems, we really have this focus also on building those and engineering those systems, right? And OC can be really considered a substantial basis for further developing qualities such as the resilience aspect, emergence, but also intelligence. Then the idea of self-awareness in computing or self-aware computing arose over many years in a variety of areas of computer science, artificial intelligence and engineering. And this idea draws mostly from theories in psychology and develops a fundamental understanding of what self-awareness concepts can mean for the design and the operation of computing systems. And basically, this is typically referencing internal state, history, social or physical environment, goals, but even a system's own way of representing and reasoning about these things, right? So consequently, I would say the notion of computational self-awareness is key to establishing this intelligence aspect and the capability of introspection. And finally, instead of following this idea of separation of concerns that is very, very typical in computer systems engineering, so you build different modules that are combined during the development process. Interwoven systems, or the idea of interwoven systems, focuses on changing the system goals that define the structure and the composition dynamically at runtime. So this kind of runtime adaptivity is a very important aspect also in lifelike computing systems. And so on the one hand, this idea of interwoven systems considers aspects of this open-ended evolution, because again, you cannot do that at design time. It dynamically adjusts at runtime in respect especially to this kind of evolving or evolutionary system composition. But it also involves social awareness, right? Because it needs to, or takes the decision basically based on the interactions with the other constituents, right? And both open-ended evolution and social awareness are key in what we consider lifelike computing systems. So these and also other initiatives and approaches clearly all relate and contribute to the idea of lifelike computing. Once more, we do not want to have another kind of a new type of initiative here. We just take this kind of different perspective, a kind of meta or holistic perspective. And obviously, all this fundamental research plays into this, and we can take very, very kind of important aspects and inspirations from all these fields. Now, how do we get there? And there being, how do we approach lifelike computing systems? Right? In order to get to this vision of lifelike computing systems, in this paper, we propose a research agenda that covers 4 important aspects. And first, and similar to what was done in successfully unifying the field of evolutionary computation, for instance, we propose to revisit existing research and technology and to integrate that into a unifying framework in the sense that we have a methodological repertoire and an architectural meta model for lifelike computing systems, right? We need to know, okay, what are the constituents? How can we use them? How can we build systems using those? And second then, and that is worth noting, that the initiatives or some of the initiatives that I mentioned before, like organic computing and autonomic computing, despite being successful, even after decades of research, cannot provide uniform benchmarks or test beds. And for example, machine learning does that, right? So there's a limited comparability in a sense, and that's also obviously mainly due to the open-endedness of the problem space. Nevertheless, we believe that for lifelike computing systems, it's crucial to consider how to establish generic test beds that provide at least for a certain degree of reproducibility and comparability, while at the same time not sacrificing the generality and open-endedness of lifelike computing systems. So this is a tricky bit, but it's very important to drive this research further. Third, and part of that basically is the success in relation to a specific utility function can only make part of the evaluation of lifelike computing systems. So we need metrics, for instance, derived in part also in organic computing or autonomic computing systems for measuring the self-adaptivity, self-organization, other self-star properties or robustness. And we need to extend them in order to be able to quantify the kind of complex inner states and workings of the systems. And also to see how these relate to broader interactions and ecosystems. And finally, we need novel computational processes and their implementations. So for instance, beyond conventional approaches like evolutionary computation, which mainly targeted at optimizing or optimization problems and automatic programming, we need new algorithms, computational models, architectures, reflective processes that rather aim at establishing the more fundamental requirement of adaptive behavior in open-ended settings on different scales really of system design. So, and I should mention that aspects like computational introspection and reflection, creativity, empathy, and social intelligence are really still in their infancy in terms of engineering systems. And as with the list of system characteristics and qualities that I discussed earlier, we do not claim this short research sketch or roadmap to be exhaustive. We rather see this as a starting point in the pursuit of a unifying research agenda towards lifelike computing systems. So we would like to see this vision grow and develop technological systems of benefit to people, and not only inspired by the living world, but also explicitly intended to replicate its qualities. And with this, I would like to conclude the talk. And I'm looking forward to Felipe's upcoming keynote, and wish you all great LIFELIKE workshop and ALife conference 2021. So thank you and enjoy.
Thanks a lot, John. Yeah, I'll do the clapping here. So great. I hope that our paper and the talk of Shaw helps to understand what we understand when we talk about lifelike computing systems, and there already were some discussions running in the chat. And even if we are already behind our schedule, I would like to take the chance for 1 or 2 questions here. But all the questions that cannot be handled in this session here, I would suggest that we can postpone them to the open discussion at the end. Nevertheless, are there questions? So please feel free to unmute and just raise your questions.
There's already one in the chat by Susan, and she asked, is this exclusively software, or do you also include hardware systems?
Great, thanks.
Yeah, I don't know who wants to answer, but thanks for pointing this out, because I was trying to read up on the chat. I didn't have it next to the presentation. And again, Tony, if you would like to answer, that's fine. But the short answer is really no, it's not limited to software only. It's actually any type of engineered system that could be hybrid, kind of robotic, social, could be software-based. So this is not limited. But it also includes, oftentimes when you look at hybrid systems, you have kind of robots and humans. But this could be also like software components, right? So that even complicates this kind of hybrid societies even more, right?
Nothing to add from my side. So is there another question? So it's fine if you post your questions in the chat, but I guess it's also fine if you just repeat it when you unmute your mic and just ask a question directly to us. Would be much easier for us.
So I might jump in then and say that I think there are 2 questions that can, and thank you very much for the talk, John. I think there are 2 questions here. Maybe we could just draw together, and I might ask Chris to comment on this, because there was a question from Susan around how does this relate to plants if we're talking about intelligence? And I've kind of answered that very briefly with some links to some ideas around plant intelligence and intelligence in trees. And I think there's a very good point there that in response that, you know, this is not the sort of symbolic reasoning we typically talk of, at least in GoFi or something like this, right? So, and then Chris comes in with, so I'm just reading the chat for those of you who haven't. I'm interested in building symbolic models of the non-symbolic reasoning methods that seem to occur in many systems. Chris, do you want to elaborate on that? Or Susan, did you want to jump in on this? I think that's a really interesting kind of discussion point.
I can do that. I can't really understand the non-symbolic methods very well, but I can understand the symbolic methods. So what I really want to do is build adequate symbolic models of those non-symbolic reasoning methods, because then I can analyze them. In other words, you know, a robot will do whatever it'll do. So will a plant. But unless I have some kind of explicit description of what it's doing, perhaps why it's doing it, and maybe even some prediction, I can't really do very much analysis. Now, it doesn't mean that any of those things are possible, but it's really a goal of mine to build appropriate analyzable models of these things, and those will be symbolic, says me. I certainly don't assume that a crayfish has its own symbolic model of anything, but it does some really interesting variable behavior.
Yeah. And I think this is the point, isn't it, that Susan, perhaps, and I don't know if you want to jump in, you're welcome to, or not, Susan, but you know, talking about this starts to overlap with you know, some of the other sorts of qualities that we're talking about around resilience, adaptation, and some of it is, that's probably a grey area. I mean, is that fair to say that there's actually these things probably start to butt up with each other, and it's not clear where the difference between those 2 sorts of things lies?
Yeah, well, I think certainly on when you're talking about learning, adaptation, evolution, they're all sort of similar mechanisms on very different timescales with underlying differences. There's an interesting way maybe of bringing those together so that we can use the mechanisms on one timescale on a different timescale. And you get an awful lot before you get into kind of reasoning. And I just wondered, because the qualities were being presented almost as orthogonal axes, that some of these things do seem to overlap. And that is absolutely fascinating. But it's just that I worked with a plant biologist for quite a while, and every time any of these arguments came up, they would say, remember, plants have got all these properties as well and are very interesting. So I always have this reflexive, when people define lifelike, checking it works for plants, bacteria, as well as animals. And then you can get a broader view. But no, this is fascinating stuff.
Absolutely. Thanks for the feedback as well. And the way it's presented, I think that perhaps isn't necessarily what we'd intended. I don't know if
I have a colleague who is fascinated by the abilities of fungi, and the kinds of things they can do, and is attempting to learn enough about those to describe the qualities so that we might be able to try that in our engineered systems. Her paper was rejected.
Thank you for this teaser on the discussion we will have at the end of this workshop, I guess. So very valuable comments, and we should definitely get back to them in our last session. And it makes me sad, but I have to interrupt this discussion now, but we have a schedule and we need to stick to it a little bit at least. So please let me again share my screen to introduce to you now our keynote speaker, who is Dr. Felipe Campello from the Aston University in Birmingham in the UK. Felipe Campello is a senior lecturer there in computer science, and he received his bachelor's in electrical engineering from UFMG in Brazil in 2003. He then proceeded with a Master of Science in Information Science and Technology, and also a PhD in Systems Science and Informatics from the Hokkaido University in Japan in 2006 and 2009, respectively. His research interests involve the integrated prescriptive data analytics pipelines, which are connecting data mining, multi-objective optimization, and decision support systems. And he applies his work to a variety of science and engineering problems out there. He's also active in protocol design for sound methodologically and statistical comparisons of optimization algorithms. He's a member of the IEEE Computational Intelligence Society, and also of the ACM Special Interest Group on Genetic and Evolutionary Computation, as well as in the Foundation of Open Access Statistics. And additionally, he's the owner of the EC Bisturi repository on GitHub. And I'm pretty convinced that he will tell us something more about this in his keynote entitled Sharks, Zombies, and Volleyball, Supernatural Computations Go Wild. Felipe, thank you very much for being here, and I would now like to pass the audience to you. Thanks.
Okay, thank you, Anthony. Thank you, everyone. Just a quick correction, I'm not the owner of the bestiary, I'm just the zookeeper. Like me and my friend Klaus Aranha, who's also present here today, we just keep that little page, but it is a collaborative effort of many tens of people just sending us their contributions. If I can try and share my screen now. Let's see if that's going to work. And this is probably the most frequent sentence for academics since last year, right? Like, let's see if my screen sharing works. So let's see if that works. Can you see my screen?
Yes.
Just the presentation or the presenter notes and all the other things?
It's working all right.
No, just the presentation.
Brilliant. So good morning, afternoon, evening, or very late in the evening in some cases to everyone. Thank you for being here. And thank you especially for the LIFELIKE organizers for inviting me to give this presentation. My name, as Anthony mentioned, is Felipe Campello. I'm a senior lecturer here at Aston University. And I'm going to have a little chat today, and I hope we can make it a lively and interactive chat about what I perceive to be kind of an issue at the heart of evolutionary computation, swarm and evolutionary computation under the wider umbrella of nature-inspired algorithms. The title of my talk is Sharks, Zombies, and Volleyball, which I hope has attracted at least some of you to this session this morning. But before we dive into what I see as a problem, and others may disagree, I think it's important that we just start with some history so that we understand what brought us to this point as well as like what are the main historical contingential reasons why the field exploded in the variety of different metaphors that we have today. And I will start much earlier than the rise of evolutionary computation or of natural computation. And I'll take us back to the 19th century. Like this gentleman there, August Kekule, was a German chemist in the 19th century who was responsible for deciphering the chemical structure of benzene. Those of us who remember our high school organic chemistry will recognize the 6 carbon atoms linked in a chain. And Kekule was a champion of visual creativity. He had a background in architecture and art before he became a chemist, and he always advocated for visual scientific creativity. And he mentioned in some of his recollections that the inspiration for him to crack that problem came from a daydream, a reverie that he was having in his chair when he started thinking about an Ouroboros, which is a little symbol, a sigil with like that's a snake biting its own tail. That's quite common in certain more esoteric communities. And that was something that this little inspiration was and has been something that was used as an example of the role of inspiration, of out-of-the-box thinking in the development of science. And of course, that's true, but there's always a however there. And the however in this case is that we don't see scientists discussing organic chemistry using snake anatomy, or we don't see them trying to synthesize new compounds by looking at what different serpents eat. And Kekule himself only went on record about his inspiration in 1890, over 30 years after the original event, at a meeting held at his honor. So he came up with inspiration, developed together with his colleagues and chemists all over the world, a whole new field of organic chemistry, and then discuss the original inspiration. Another common example is Elias Howe, who was an American, I think he was American, inventor, also in the 19th century, who was the first person to be granted a patent for the lock-stitch sewing machine in 1840. And when he was designing with his team, the lock-stitch machine, he had a particular challenge in the design of the needle because they couldn't find a design that worked. And Elias is claimed to have come upon the solution after a nightmare in which he was being chased by a tribe of angry cannibals, demanding that he finish his machine and threatening him with hollow-tipped spears. And he woke up and Eureka, had a click and placed the whole of the needle at the tip of the needle rather than the bases, and was granted a patent, became a millionaire, etc. So another good example of inspiration coming from a completely unlikely source. However, we don't see engineers today discussing their equipment in anthropological terms or trying to design better machines by examining the habits and culture of isolated tribes. The inspiration came and provided the necessary ideas to develop, but the language of the inspiration became something of a history of the lore, not necessarily percolating into the area itself. The dream story also only appeared years later, decades later, as a family recollection. And I think like my point is probably already across now. Throughout history, scientists have drawn inspiration from many different sources: natural world, dreams, personal experiences, anything. And lots of interesting concepts were also developed within computer science based on different ideas from the natural world, from different phenomena, to devise innovative ways to solve problems. And I will just place that under the general umbrella of optimization, although there are different problems that have been solved with nature-inspired methods, to model and simulate natural systems to gain better understanding of those processes. And unlike when you're trying to solve a problem, when you're trying to simulate something, you want to be as faithful as possible to the underlying phenomenon so that you can ask what-if questions and examine different paths that that particular phenomenon could have taken. And also to generate art and music and generate some sort of computational creativity. And this is a strength. This is not a problem. And that's something that I need to clear out at the beginning of any conversation that I have about the bestiary and my little pet peeve with the area of metaphoristics, is that people usually understand that I'm arguing that the problem is with the inspiration, and nothing could be further from the truth. The inspiration is fine. The problem is how long or how far do we take the inspiration before we start actually discussing the problems that we are trying to solve. And with that, I just want to mention also that I'm going to concentrate most of my discussion here on the first bullet point of this list, on the solution of problems. I'm not someone from the modeling and simulation of natural systems crowd. I don't have a background in art or music. I can barely draw a stick figure. So my focus is going to be on the nature-inspired methods for solving problems, optimization problems, machine learning problems. And this has happened, like nature has inspired quite a lot of very successful methods throughout the history of computer science. We've had even before it was computational, in the 1950s, George Box, which was one of the giants in statistics and industrial engineering in the 20th century, he came up with the evolutionary operation, a method for increasing industrial productivity that had some relationship with how evolution and natural selection and selection in general work. Then you have Bremerman with what could be considered the precursors of genetic algorithms in the early 60s, optimization through evolution and recombination. You had Hans Boll-Treffel with evolution strategies, Larry Fogel with evolutionary programming, John Holland with the landmark book on adaptation in natural and artificial systems, in which not only the basic building blocks, no pun intended, of genetic algorithms were laid down, but also some attempts at explanation of theory were also put forward for discussion. You had Kirkpatrick and Gallant coming up with simulated annealing in the early 80s, taken again after yet another natural metaphor, the cooling of metals and the structuring of crystals, which is actually trying to reach a state of lower energy. Not trying in the intention way, but that's what usually happens when you're annealing or cooling down something over time and slowly, and reheating and cooling, etc. You have Farmer and Packard and Perelson in the mid-80s with a immune metaphor, not only to understand the immune system, but also to see how it could be used to solve certain problems. You have particle swarm in the mid-90s, you have ant colony in the mid-90s. So lots of inspiration, lots of different methods, many of them very successful, advancing our knowledge of how to solve particularly difficult problems that didn't conform with the assumptions of mathematical programming. But critically there, despite sometimes lacking in a theoretical background and with experimentation leading on theory, there was generally good scientific process being followed. You had the general inspiration, you had the discovery, the click, the serendipitous observation of a phenomenon as probably being a good idea for solving problems. You had the testing of those ideas, the adversarial testing of those ideas, not only against similar methods, but against what could be considered state of the art for the solution of certain problems at the time. You had community analysis and feedback, adversarial community analysis and feedback, because as I'm going to mention later today, there has been some community feedback, but not always adversarial in a lot of the nature-inspired math heuristics community. And you also had clear benefits and outcomes. And this made those methods, this made those ideas subject to the scrutiny and to the exchange of concepts that make up good science. But unfortunately, they also sowed the seeds of something that came to become a problem, came to be a problem, because on top of following relatively good scientific practice, most of those methods, they retained a lot of the metaphor-specific language in the description of the methods. Although it was not critical for the workings of the methods, the language was there, and the recipe was done for things to begin to change in the late 90s and early 2000s, which takes me to part 2 of my talk, which I named The Age of the Metaphors. And at some point in the late 90s, early 2000s, the mentality of a part of the community in optimization math heuristics started to change. And I'd like to illustrate that with a little personal anecdote. So in the early 2000s, I was having a chat, and that is me, by the way, like 20 some years younger, and looking particularly bored for a reason. I was having a chat with with one of my mentors, walking down the campus of UFMG in Brazil. And we were part of an applied optimization group on the area of electromagnetic design and electrical systems. And my mentor turned to me and said, Felipe, you need to find some new natural phenomenon, some new natural metaphor, and develop your own algorithm. That's how you'll get famous. That's how you'll get a lot of citations. That's how your name is going to become a household name in this area of evolutionary computation. You need to find your metaphor. Just don't worry about genetic algorithms. Don't worry about particle swarm. Invent your own. That's how it works now. And unfortunately, or fortunately, I never got to invent my very own metaphor-based meta-heuristic for a variety of reasons, and not for lack of inspiration, but maybe for a sense of scientific adequacy, or for just because I was not creative enough or not bold enough. You judge that. But others did. Quite a lot of others did, and in increasing numbers throughout the years. So at the beginning, in the beginning of the 2000s, and I place the line there around the year 2000, simply because it's a convenient place to put it. It's not because like before 2000 all good, after 2000 all bad, because those things don't happen as sharply. They're usually part of a continuum. The community moves with certain inertia. But around the year 2000, we started seeing more and more of those examples appearing. Some of them still bearing some relationship to a process that could be seen as optimizing something or solving a problem that was related to the problem that people actually wanted to solve. Some of them slightly more exotic. So we had, but it was still like 3-4 per year, so it was still manageable. It's at that time you start seeing algorithms based on wasps, or musicians playing jazz, or like several different types of bacterial phenomena, and honeybees tended to be very popular. Between 2006 and 2007, notice that the previous list was 5 years, 6 years actually. This one is 2 years. We started having a slight shift and seeing certain phenomena that didn't necessarily optimize anything. So the metaphor started being stretched a little bit with algorithms based on parliamentarism elections or imperialism or small worlds or plant saplings. And again, just to reinforce my earlier points, there's nothing wrong with trying to simulate those phenomena. And I'm pretty sure we can learn quite a lot of interesting things by simulating them. The problem is that the authors of those methods were not simulating those phenomena, and they were not doing good optimization either. They were simply starting to develop new methods. They were following the advice of my mentor. I can say for all, but at least for some. And then things started getting a little bit more numerous. And notice that I reduced the font size of my list here. And we started having things like intelligent water drops, or dolphin partners, or group counseling, or slime molds, or fish skulls, and glowworms, and all sorts of different metaphors. And we started having about 8 or 9 per year, and then another couple of years there with over 10, so about one every month, with consultants and bats and reincarnation and catfish and electrons flowing and teachers and mosquitoes laying eggs and all sorts of different metaphors. And by then it stopped really being funny, because up to now we were making fun of this, but it started looking like something that was being exploited. And then of course things exploded. And between 2012 and 2014, in these 3 years, we had over 60 different metaphor-based methods, approaching 70, and all sorts of different things, and small variations of the same theme being claimed to be completely different. So we had regular wolves and gray wolves. We had several different types of bees. We had ecogeography. 2014 was World Cup year. So we had 2 different groups claiming to develop a soccer tournament-based method. We had colliding bodies and cockroaches and chicken swarms and rays of light and hoopoe, which I had to Google, it's a type of bird, and blind naked mole rats and cuttlefish and dolphin echolocation. So all sorts of crazy metaphors. And it just kept on going and going with killer whales, binary whales, orcas, which are somewhat different from killer whales, and whale echolocation and all sorts of different things. Mosquitoes flying, which are different from mosquitoes laying eggs, and jaguars and general relativity and flying elephants and regular elephants and all sorts of camels and crows and a whole bestiary. And that's when Klaus and me came up with the general idea of cataloging those things and to try and at least have a laugh out of the whole madness that seemed to take hold of the area of meta-heuristics. And there are like some of like I'm going to mention some of my favorite later, but you have things like based on donkey theorems and meerkats and emperor penguins and regular penguins and all sorts of crazy things, and barnacles as well. And by now, I hope you're all asking yourselves, are there really 260 plus and counting different ways to build population-based meta heuristics? And that's a good question if you think about it, because certainly some people have thought it worth their time to put forward a new novel algorithm, or as it's usually the case in the abstract of a lot of those papers, a novel computational paradigm for solving optimization problems. But are there really 260 plus different ways, fundamentally different ways to justify a new metaphor? And you be the judge. What I can say is that, like, as early as 2006 and earlier than that, actually, people were already advocating for a unified approach of computational intelligence in the little context of meta heuristics of evolutionary computation. And if you think about it, like the basic recipe is not terribly difficult. What you need to implement an evolutionary or swarm algorithm is an initial sample of your space, which we can call a population or whatever, a reproduction function, or first an assessment function, reproduction with variation, and a way for you to select how to compose the next sample. So it's an iterative adaptive sampling procedure. And you can, and many people have done, you can stratify that in a number of building blocks that are relatively simple. And all those methods can be seen as small variations of a basic template. So whether or not it's worth calling a vector a bee or a soul or a musician, I leave it up to each one's judgment. The second question that probably we should be asking ourselves, is that really a problem? Because what of it? Like, if people are finding inspiration anywhere, just let them do it. And my view of this particular phenomenon is that, yes, this is a problem for a variety of reasons. And not only because I'm a grumpy old researcher who never got to invent their own algorithm, but because this, at least in my view, and which I know is shared by some of our colleagues, it actually impedes progress in the field for a number of reasons. First, fragmentation of the literature means frequently reinventing the wheel and sometimes not admitting it. And I can relate to that firsthand, because even though I didn't invent my very own metaphor-based algorithm, for the first years of my career, of my academic career, during my master's, my PhD, I was very much immersed in one specific community of a certain metaphor there. And we were very defensive of the uniqueness of that metaphor. So some of our reviewers would come back to us and say, like, oh, like, this method that you're advocating is just a variation of a particle swarm optimization. And we will come up with the most subtle differences and explode them and say, no, this makes it absolutely unique. When in fact, we were enamored with the metaphor, not necessarily with the optimization algorithm. And again, no problem being enamored with the metaphor if your goal is to understand and simulate that metaphor. But in our case, at least explicitly, we wanted to solve optimization problems. And for that, this fragmentation meant that we didn't use the developments, the theoretical and experimental developments that had happened in other areas to actually advance our own research. We were constantly walking sideways rather than making progress. And this is not an exclusive trait of the metaphor that I was working with. Throughout the years, several authors have done theoretical analysis of some of those algorithms and came to the conclusion that they were actually special cases or special configurations of pre-existing algorithms. Some of these algorithms pre-existing for 30 years. So there has an element of this fragmentation impeding progress. There's also the issue of mutually incompatible metaphor-specific language being another unnecessary obstacle to progress, not only because you're fragmenting your literature into 260 plus different small islands, but also because you're using mutually inconsistent language. So you have a vector in the space of real numbers. You don't call that a vector. You call it a cuckoo or a mime or a bird or a barnacle or a water drop or a zombie or a volleyball player or whatever it is. And the language permeates the whole description of the algorithm the whole illustrations of the papers. You read some of the papers, as I'm sure many of you have, and you will see figures discussing all sorts of different things that are tangentially, if at all, related to the problem that's trying to be solved. So you have things like descriptions such as the objective function is regarded as a transcendental entity in the space-time, or the aim is to use new and potentially better solution, cuckoos, to replace not so good solutions in the nest. Or one of my personal favorites, the selection of two barnacles is based on the length of their penises. And what is the relationship between barnacle phallus and an optimization process is something that I leave to your imagination. Another problem that I see with this whole thing is that, and this is not exclusive to the metaphor-based literature, but it's the issue of poor methodological standards in the validation and comparison of this method. And this is an area that has had good practices documented for it, at least since the mid-90s. And in the early to mid-90s, you had a couple of papers by John Hooker claiming for an empirical science of algorithms and denouncing how we had it all wrong with the testing of heuristics. We have critical notes by Ivan and Gelasity in the early 2000s. We have a paper by Barr and collaborators in 1995, laying down the basic framework for designing and reporting computational experiments with heuristic methods. And the problem remains not only that the experimental design is poorly done, but that the comparisons themselves are done with generally, and again, I'm generalizing here, but in most cases, or in many cases at least, it's done against only against other methods that follow exactly the same general approach. So we will see the algorithm for, and I'll just make this up here, the dirty laundry algorithm that is going to compare against the clean laundry algorithm and the can I maybe use it again laundry algorithm, but never comparing against what is actually the state of the art for that problem. And if you have 5 algorithms that all of them perform poorly, it's not that difficult for you to beat the other 4. And so there is an element of poor methodological standards there as well, which tends to, again, unnecessarily impede progress and increase the noise to signal ratio in the literature. Finally, there's the contamination of other fields that are not necessarily dedicated to the design and examination and development of metaheuristics, but fields that look at the field of metaheuristics for inspiration, for solution strategies to their problems. And we see that happening in quite a variety of fields. And some of the most absurd of the metaphor-based algorithms are originally published in application journals, because the editorial body there, the reviewers, do not necessarily have the know-how to judge and to understand what's going on in the area of metaheuristics. And of course, there's a little mea culpa there in the middle of those papers, because there's one of my papers there in the bottom right from when I was a master's student, a clonal selection algorithm for optimization in electromagnetics. And that is the paper that one of the reviewers mentioned that maybe you want to express that as a PSO. And we got very defensive about it. And it passed, it got published. And not because it was a fundamentally new way of solving a problem, but because the editorial body, with the exception of that one reviewer that just let it slide and approved the paper after the second round, the editor-in-chief, the other reviewers didn't know enough about the metaheuristics community to make a good case against, okay, you know what, like stop talking about antibodies and talk about optimization strategies. Fortunately, at least from my view, I grew out of it. And final, why are so many people doing it then? So if this is a problem, and if there are so many issues, why are there so many people developing all sorts of crazy algorithms based on tangentially relevant metaphors? And this is a complicated question, of course, and I cannot be in anyone's mind, but I have a few guesses. The first one is the structure of perverse incentives, and that is not exclusive to our area of research. There are perverse incentives in academia, in every field really, but this explains at least a bit why people are desperate to publish anything. And that, coupled with another point that I'm going to mention in a couple of slides, may explain part of it. There is a very interesting paper by a couple of environmental engineers, but that could have been published in one of our journals, for its relevance and adequacy to the discussion. It's called Academic Research in the 21st Century, Maintaining Scientific Integrity in a Climate of Perverse Incentives and Hyper Competition. And they list some of the issues that academic communities in general are facing now, and that are leading to this deluge of relatively low quality, tiny incremental papers, salami science kind of papers. And the first one of there is researchers are rewarded by increased number of publications. If you publish a lot, you are rewarded by it, be it in terms of reputation or career advancement. And these may explain a little bit why it's so important for you to invent your own method, call it your own, so that you can reap the successes that come with it, even if you're at the bottom of it, not necessarily advancing the field. Second one is a lack of a methodologically sound tradition in the field. And this is changing, fortunately, in the last decade or so. The field of meta-heuristics has been advancing in terms of its methodological standards, and lots of journals and conferences are getting better at it, and lots of authors are also getting better at it. But there wasn't a methodologically sound tradition, and there was a soft spot, a little open flank in the area that had a soft spot for all sorts of metaphors. And as long as the metaphor was interesting, it was not necessarily, it was not a necessary condition for publication that the method itself was interesting, or that the metaphor was being adequately simulated. And that leads a little bit to sort of cargo cult science, where people like go through the motions and they do experiments and they write papers, but actually the scientific advancement is not necessarily there. But if you ask me, I think the main reason why so many papers have appeared and so many different methods have popped up in the literature with all sorts of metaphors is because it's very easy. It's very easy to publish. It's becoming increasingly difficult in the top journals and conferences, but it's still very easy to publish your new metaphor based, and you don't need to actually go through the motions of developing a sound framework or a really innovative way of solving a problem, as long as you are creative enough in bringing up or picking up a new metaphor. Just as an example, there is this paper that was published a couple of years ago, KU Battle of Meta-heuristic Optimization Algorithms, in which a group in South Korea sat together and they developed 6 new methods just like that. And if you think about it, it's not particularly difficult. If we all put our minds together here today, and if we were in the auditorium, I would suggest that we do this exercise. We could probably invent a new metaphor-based algorithm today and call it the conference attendee metaphor. And we could say that conference attendees are trying to maximize the entertainment value and the information value in the sessions that they attend. And they would talk to each other, so information would be passed and they would flock. And as soon as enough people were attending a talk, more people would converge to that place. So we could say that the local optimum is an interesting talk. And just like that, we could invent a new meta-heuristic and publish it and maybe get hundreds of citations. But we wouldn't necessarily be advancing the field by doing that, because what I just described is a variation of particle swarm optimization. We can essentially just switch the metaphor and have the same method. And it's very easy. The potential personal rewards are big and the risks are small. And some people make a career of it. So I took the first 10 or so papers from a Google Scholar profile. And the same researcher has come up with the gray wolf optimizer, the whale optimization algorithm, moth flame optimization, antlion optimization, sine cosine, salt swarm, dragonfly, grasshopper, multiverse, Harris Hawk, and the multi-objective gray wolf optimizer, which is a variation of the first one, so I will not count that one as a novel one. But the same person came up with more than that. These are just the 8 or 10 initial ones. And if that suggests to you that this may be a particularly creative person enamored with the natural world that sees different methods everywhere that he looks, my alternative hypothesis is that someone that actually found a way to publish and get citations relatively easily. And when I say relatively easily, and when I say the rewards are big, they are big. You look at the citation numbers of those methods, you have 6,000 citations, 3,500 citations. And at least for 2 of them, it has been already shown and published that they are special cases of evolution strategies, which is an optimization method that has existed for 40 years now. So does it deserve 6,000 citations or 3,500 citations if it is a rehash of an existing method that is a pretty decent method, not state of the art in its original form, but it's a pretty decent method that can solve problems. But just renaming the terms of that algorithm and republishing it, is it worth that amount of citations? You be the judge. So we have a problem, we have a mess. And the question now becomes like, how do we fix it? And the short answer is that I don't know. I have absolutely no idea how we can fix this, because it gets to problems that are like larger than any individual action. It gets to the incentive structure in the publication, in the peer-reviewed publication area, or peer-reviewed publication community within the area. It gets to improving methodological standards. I don't have an answer to that. But other people, more creative, better researchers than me, they have had some ideas that are having some success in dragging us out, at least from the best conferences, best journals, and starting to propagate to the wider community. There is some pushback to this. And one of the ideas is standardization and metaphor agnostic modeling. And this is something that resonates quite well with the paper by Helena I'm butchering the pronunciation, sorry, Helena, by Helena and her co-author that comes just after this keynote with the module-based modular assessment of meta-heuristics. And the idea is that you can have as many methods or as many nature-inspired meta-heuristics as you want, as long as they are described in a standardized metaphor-agnostic way, so that we can easily notice their similarities and differences. And when you start doing that, and there were like 6 years ago-ish, there was this little manifesto in the Meta-Heuristics International Conference called A Research Agenda for Meta-Heuristic Standardization that advocated precisely that. And earlier this year, Jessica de Armas and her co-authors, they published a paper where they are developing metrics to quantify the similarity in meta-heuristics. And when you can quantify similarity, even if the meta-heuristics themselves are described in like metaphor-based terms, but when you can quantify similarity, you can do what I did with their table 5 or 6 in the paper, which is to cluster the methods and detect their similarities and see what is closer to what. Because then you can focus your attention when you're faced with a new meta-heuristic and say, okay, this is the one that looks to be the most similar. Let me check that to see if these people are not simply reinventing the wheel here. And you can do that with your own method as well. If you're developing, if you came across a particularly clever inspiration that you think is a completely innovative way to develop a method, you can actually be adversarial against your own ideas and filter them by essentially looking at an increasing amount of methods and say, okay, like this already exists, this looks like that, so let me just build upon whatever has already been done for that particular algorithm. So standardization and the use of metaphor agnostic language, in my view, is an essential aspect here for us to start dragging ourselves out of this mess. Another one is better editorial practices. And this has started to become a reality as well. So several different journals and conferences as well have started asking the authors and demanding that any new methods be described in metaphor agnostic terms. It can come from wherever natural inspiration or supernatural inspiration, like the zombies or reincarnation algorithms, as long as you describe your method in a language that everyone can unequivocally understand, so that the reviewers can look at that and examine more easily without being unnecessarily like confounded by the metaphor language. So lots of different journals have started doing that. Some of us have written an open letter that it's going to editors-in-chief, specifically for application-based journals, to try and bring that to the attention of people, to say, okay, like there is this problem, you may want to check that, and you may want, whenever a new paper comes to your journal, you may want to ask the authors to describe that method in metaphor agnostic terms. Another one is eternal vigilance, and as the price of freedom, as the saying goes. And that goes from the post-publication reviews from the community. And if the community does not accept any new method simply because the metaphor refers now to tunicates rather than crayfish, it starts getting like the incentives start going a little bit down. The perverse incentives, I would say, start going a little bit down. And also in the literature, to actually call on the methods and show which methods are actually just rereadings of existing ones, so that like the community as a whole start being a little bit more aware of this issue. And there, as I said, there has been quite a lot of pushback against the worst practices there. Just to wrap this up, because I think I'm getting close to my time here, and tying back to the beginning of my talk, inspiration from whatever source, it's good. It's not a problem, and that is not the issue in the meta-heuristics literature. Inspiration can and will come from anywhere, and that's a strength, not a problem. Experimental development before theory, no problem, as long as the experimental developments follow good scientific practice, as long as the experiments are well designed, the comparisons done against the state-of-the-art methods in the literature rather than marginal variations of the same method. The experimental part preceding the theory, it's not a problem, and that's not an exclusive trait of computer science. That goes for physics, where experimentation has led on theory on several fields. That goes for chemistry, that goes for any of a wide variety of areas. What is a problem is sloppy science and exploiting the publication process, exploiting weaknesses in the publication process to actually just gain that lot of citations or gain undue recognition. Just then, so that we end on a bright side, just so that I don't end on this doom and gloom kind of note, there may be a good side to this whole madness that has gripped the field for so many years. And that is that the age of the metaphors has forced the field of meta-heuristic to reflect upon its own practices. It has forced the field of meta-heuristics to start developing, to focus on developing more methodologically sound practices, a more criterious publication process. And these may help us transition to what Sorensen and Sevaux and Glover discussed in their chapter, I think last year or the year before that, the history of meta-heuristics. They called the new chapter in the history of meta-heuristics the scientific period of meta-heuristics. And the age of the metaphors may have helped accelerate that. So we may still have something good coming out of this whole mess that has been the field in this last couple of decades or so. And with that, I come to the end of my talk. Thank you very much for being here. Thank you very much for your attention. A special thanks to Kenneth Sorensen and Ruben Ruiz, who have shared some ideas for the talk, to my partner Klaus, who is, I see his little face in the camera there on the side, for this fantastic partnership, and also for being such an awesome all-around guy, and to Aniko and Peter Lewis, Peter for the invitation, Aniko for some feedback that she gave on those slides. So thank you very much, everyone, and I give the word back to Anthony. Thank you.
Thank you very much, Felipe, for this great and thought-provoking talk. I will act again as a surrogate here and clap my hands for all of the audience. Thanks. So we have plenty of time for questions, and I'm pretty convinced there are some out there. So please, again, feel free to unmute your mic and just post a question directly to Felipe. And before we start with the Q&A, I'd like to make a suggestion. I love the chat and what it's going there, and some loss also happened, I guess. But we also have this Slack channel, and I post the link here. So if you want to ask a question to the current speaker, I would ask you to please put your question in the Slack channel, and then you can get chatting and all this stuff and writing here in the Zoom chat. hope this works, and we'll have an eye on both channels. Okay. So just as a quick remark, and now I'd like to open the discussion. Any questions?
Yeah, thank you very much for the talk, Felipe. Very, very interesting. I asked myself, and I think Klaus already mentioned it in the chat. Is there something that you could see the effects on the co-authorship graphs or the citation graphs if you analyze the contributions, in the sense that everybody is talking about his own niche and doesn't look over the boundaries of the niche? So I agree totally with you that papers, there's such a vast amount of papers that it's just not possible to know everything. But I think that everybody tends to work in his niche, and that is part of the problem.
Yes, I tend to agree. And as I said, like this fragmentation of the literature, it has been happening, and it tends to reinforce this niche phenomenon, right? Because if you have the little community that deals with like fireworks algorithms, which tends to be a quite lively community there, and they tend to do development only within the fireworks. When they go outside, they compare with other types of metaphor, like gray wolf or moth flame or whatever it is, but it never gets much beyond that. I actually tried. I didn't have the time, unfortunately. I started writing the scripts to mine the citation networks of all of those papers, and I have the DOIs already. So this analysis is halfway done, but I couldn't finish it in time for the talk. But that is a question that's definitely interesting, and that would allow us to answer a couple of other questions as well. First, whether or not there are citation cliques, like people who tend to mutually cite a lot, and that would explain some of the absurdly high citation numbers that some of the metaphors tend to receive. Whether or not there's this island effect that we like see anecdotally, but we don't have the numbers yet. What is the effect? How much of this leaks to application journals? Again, we know this anecdotally, but it would be interesting to see the numbers. So the analysis is halfway done, but it's something that's definitely interesting, and it may explain quite a bit of the phenomenon as well.
Yeah, thank you very much.
Oh, thank you.
There's that was a really interesting talk. I've been worried about that issue for some time. There's an anthropological result, if you can call it that, that humans tend to be more comfortable with groups of size 50 or so, and not much larger than that. And that any groups larger than that tend to fragment more or less automatically. So that you can have two different groups of people studying exactly the same subject with exactly the same methods that don't know about each other at all. We've had this happen multiple times in the self-awareness community.
And it happened with in the early days of evolutionary computation as well. You had the European school and the American school developing in semi-independence until the late 90s. And I totally agree that may explain a bit, but the same, like this being an anthropological result, it wouldn't be exclusive to this area. And we don't see the same type of fragmentation in the nomenclature in other areas of knowledge, at least not to the same extent that we're seeing here. So we don't see chemists referring to bonds or atoms or molecules using mutually inconsistent language, even if the small groups that are investigating different aspects at the forefront of knowledge there may develop works in relative isolation for some time. But I don't see that explains everything. It may be part, it's multifactorial in the end, as any complex phenomenon. But it may explain part, but I don't see that being a good excuse for the sorry state of fragmentation that we see ourselves in the meta-heuristic community.
Thank you. Further questions?
There is this question in the Slack.
In the Slack? Ah, great. Okay.
Okay, if anyone can read that out, because I closed the Slack
Yes,
not to
sure.
be distracted with the notifications.
I think it's a remark, but then I just read it. So another remark to the talk by Sven, our co-organizer. It is not necessarily bad to reinvent the wheel in all cases. Part of the scientific process toward knowledge in the field always follows different tracks, from which several turn out to be wrong. And if authors are not aware of their new method, reinventing PSO, telling them is also part of the process. So how can you distinguish between misguided through wrong incentives and just usual wrong paths towards a correct goal?
We can't because we can't be in anyone's head, right? And we don't know what exactly is driving each author. But yeah, I totally agree. Rediscovering things is part of the scientific process. And it will happen whether or not we use metaphor agnostic language and we start referring from today, if we start referring to vectors as vectors, if we start to referring to objective functions as objective functions. So even if that happens, there will be some element of reinventing the wheel simply because the field is so vast that you cannot be aware of every single paper that exists. But if the language is common, it makes it easier as you progress with the reinvention of the wheel to actually pick up on the threads from the different track that developed there. And notice, oh, by the way, I have been working on that. This other group in Luxembourg or Papua New Guinea has developed something very similar a couple of years back. Let me just grab onto that and see if their results can advance my own research. Because understanding that there is similarity will, it can result and will probably result in the ability to reuse results from other areas more easily than if you simply isolate yourself with obscure or metaphorical language. So I don't see the reinvention being a problem. The amount of reinvention, it may be, because it means that the field is only moving sideways and it's not necessarily progressing, so a lot of energy gets wasted there. But it could be minimized. It could be better structured there. Someone has their hand up,
Yep,
I think.
That's me. Hey,
you don't get to ask. You don't get to ask any questions here.
No, I actually want to bring like a discussion that we having on the chat that I think it's quite interesting, which is comparing what is happening in meta-heuristic optimizers, in particle swarm optimizers, with what happens in the neural network world. In machine learning, we have like all sorts of networks with funny names. We have like YOLO. We have like, I don't even know the name because I'm not really a machine learning person. But even though the networks have funny names, they still kind of use the same terminology when they are describing their processes. So you still got regularization that everyone uses. You got like the dropouts that everyone uses. What we see here in the meta-heuristics lens is that cuckoos, they have nests and the particles have velocities. And we have like fireworks, they have gravity.
Zombies have brains.
I don't know because I don't remember the zombie paper, but what I'm saying is that it's not only the name of the, if it was only the name of the metaphor, I think that would even be fine. The problem is that they use different names for more like fine-grained things, which kind of makes it hard to compare them and to understand one metaphor in the name of the others.
And it's an additional unnecessary layer of translation that needs to happen when someone is reading a paper, because you're coming from a paper. It's suddenly you have to switch from thinking about antibodies to thinking about wasps or to thinking about fish, and it's an unnecessary layer that people have to actually get past to understand what's going on underneath. And if it's unnecessary and like it shouldn't be there. Yes, of course, neural nets have little or nothing to do with brains. Yeah.
Okay, thanks again for the discussion. And I think there are much more questions out there. And I can once more only refer to the Slack channel. Please remember your questions, write them there, and we will have time at the end of the workshop to follow up the discussion on that topic. Felipe, a huge thanks for this really, really great talk. And again, I act as a surrogate. Thanks.
Thank you very much. Thank you, everyone. And I pass the mic to the next presenter. So thanks.
Yes, exactly. And the next presenter is Helena Stecker from the University of Augsburg. She is a former colleague of mine, and I'm very happy to have her here. And she will tell us something about the analysis of meta-heuristic components, which fits quite well, I say. It's the next talk after this stimulating keynote. So Helena, the audience is yours.
Yeah, thanks. Can you see my screen? Perfect.
Yes.
So yeah, in perfectly fitting after our great keynote, I now want to present our position on the necessity of analyzing meta-heuristics in a component-wise manner and our corresponding research agenda. So we're motivated by the question which meta-heuristics are suitable for a given optimization problem. Of course, with a small exception that when we cannot or do not want to use any sort of automated algorithm selection, but we want to base our decision on the knowledge we have on the meta-heuristic algorithms. So first off, another additional factor for answering this question is that we have to define the goal that we want to achieve with our optimization. For example, if we want an optimization algorithm with an extremely short runtime, but maybe that does not find the global optimum, or if we want to find the only high quality optimal values for our problem. And on the other hand, we can decide if we want to use one algorithm for exactly one specific optimization problem and want to have a tailored algorithm, or if we want to use the same algorithm on different problems so that it still works at least okay, and that's enough for us. So altogether, this decision process usually requires extensive or expert knowledge, or needs a lot of trial and error. And the whole thing even gets more difficult, as we have heard, by the large amount of metaphor-based meta-heuristics. And these make it extremely hard to detect if there is any suitable strategy for my problem, or if there are new innovative approaches with new advantages, because even if the metaphors are quite useless, it might be a good variation of a given meta-heuristic. And we might need to use it, but it's hard to detect. And so what is a common strategy for this type of problem is just using the same algorithm over and over, no matter if it fits for the problem or it doesn't. And altogether, we think that the assessment of meta-heuristics in terms of their functionality, performance, and behavior needs to be facilitated to give any clues on how to choose a meta-heuristic algorithm. So what we propose is a way we can gather additional information on meta-heuristics to alleviate the problem of selecting a suitable strategies. And this is especially helpful, of course, for new approaches to analyze them in a non-metaphor related setting, but also, of course, existing approaches can and should be included in these analysis as well, so that we can see the differences and that we can relate new strategies to established ones. Altogether, we would structure this this procedure into two analysis phases. That is, for one, a conceptual analysis and an additional empirical analysis. And we want to base both analysis strategies on a unified framework for meta-heuristic algorithms. So this concept has several goals. That is, for one, to gain an overview of what is there in terms of meta-heuristics. And in this case, what operators do they use? What features do they possess? And how do they perform and behave on specific search problems? And also, if we have this set of components of meta-heuristics, we can test new combinations of those. If we know two things that work well, we can combine individually, we can try to combine them. And in the end, we would have some kind of knowledge base on the behavior and the performance of meta-heuristics that is not focused on any metaphor and would use consistent implementations. So first off, we think that a unified framework for meta-heuristic algorithms is a essential basis for this type of analysis, because there is a constant demand for standardization, reusability of meta-heuristic strategies, but also for the knowledge of the specific components and a consistency in the description of the algorithms. So this some kind of unified framework can provide a common basis for conceptually analyzing meta-heuristics, but also for their implementation and their empirical analysis. And usually meta-heuristics are similar anyway, at least in some general structures. And we can see an example of how a component structure of a meta-heuristic would look like, and especially the sequence of selection, generation, and replacement and update is the most common theme in all meta-heuristic algorithms. Of course, it might be possible that there are some approaches that do not quite fit, but at least we haven't encountered any yet. And with this system, we can structure meta-heuristics as we can differentiate between meta-heuristics in terms of the operators they use for the specific components. So there are several possible operators for the selection of the new solution or the solutions to be changed. There are several different operators that can be used for generation and for all other of these main components. And so we can say that a specific meta-heuristic algorithm is determined by the individual operators it uses in these components. And of course, one component could use, or there could be several operators related to one component simultaneously. For example, for genetic algorithms with mutation and crossover, which both belong to the generation component. So we want to keep this as a basis in mind. And now, talk about what we want to gain by the analysis and how a conceptual and empirical analysis could look like. So first off, what influence has a conceptual as well as an empirical analysis of meta-heuristics on the decision which algorithm to use? Conceptual analysis means that we want to find common features of meta-heuristics. That some kind of abstract high-level description of certain characteristics. And so if we have this kind of operator or component or even whole algorithm specific features, we can present them in relation to the meta heuristic we look at, and get a really fast initial overview on what it should do if we apply it. And then the next step would be the empirical analysis, or looking at results from empirical analysis, which then specify how does this meta-heuristic algorithm we look at really behave on certain optimization problems. So maybe we can then relate our problem to these test problems and get at least any idea on the suitability of this algorithm. But then we have first to decide what is important for when performing a conceptual analysis and building this kind of information database, and of course do the same for the empirical analysis. So as for the conceptual analysis, as the main goal is relating the components of meta-heuristics to common characteristics, we would classically use criteria that are, for example, also common to these typical meta-heuristic classification systems. They describe in an abstract way, for example, if an algorithm uses any adaptive strategies, or if maybe we want an inherent elitism mechanism in one of our components. So if we analyze the existing meta-heuristics according to these criteria, we can get some kind of small profiles of strategies inherent to different components. And altogether, this again helps to gain a short overview of different meta-heuristics. And as I said, selecting meta-heuristics with certain features is facilitated if we do, for the beginning of the selection process, if we do not want to look at performance right away. And yeah, we have these profiles. So the next step then is gather results on the performance and the behavior of meta-heuristics. And especially the behavior part is extremely interesting. Performance analysis is done quite often, for example, in typical benchmarking studies. But the behavioral part is only in the focus within the last few years. And analyzing the behavior in a unified approach and not focused on, for example, evolution strategies or only of the behavior of different operators for genetic algorithms or something like that is quite rare at the moment. So this empirical analysis should then use the unified framework for consistency in implementation and the easy exchange of operators, and should focus then on trying out different operator combinations and relate the performance of the different operators to, or relate the effects of the different operators to the resulting performance and behavior during the search. So in summary, we would gain of course, general knowledge on the different operators used. But we could also specify and quantify the capabilities of a meta-heuristic algorithm more directly, and it would all be independent of a metaphor. So to sum up the advantages of this threefold approach on how to look at meta-heuristics component-wise, they could help to structure the field of meta-heuristics by determining common features, but also by enabling a systematical analysis, and especially the empirical analysis would provide information on problem-specific performance and behavior, which is definitely still not extensive enough researched area. And if we have this unified framework and use it for the analysis, we have consistent implementations of the algorithms, and we can easily exchange their features and test new combinations that haven't been tried before. However, there are some problems, or at least some questions that need to be answered on a way. For example, if this component-oriented approach is really feasible for all meta-heuristics, if there aren't too many that can't be dissected component-wise, or if the empirical analysis isn't just too large. It's extreme. If we view as many meta-heuristics as possible, and evaluate all operators almost individually, it's a lot. Yeah, it takes a lot of time, and it will provide a lot of data, and that needs to be structured. Furthermore, and that directly relates to the meaningfulness of the results, and the contribution to the meta-heuristic selection problem, because if it's too much data and too little information, or it can't be, excuse me, it can't be presented properly, then it would be a waste of time. And so this also, for the last point, there is the issue with theoretical approaches. There is some kind of discussion if the focus should be on providing more theory instead of empirical studies. So it's rather an abstract question that probably cannot be answered directly, but it is an issue to keep in mind. Sorry. So to sum it up, we provided a strategy to analyze meta-heuristics in different degrees of detail. Sorry. By utilizing a unified framework. Excuse me, I think my throat is too dry now, but I try to make it short. And and we presented our research agenda, how we plan to analyze existing approaches and new combinations to gain more information. And the next steps, well, I already told you that there is a focus, or there is a shift towards focusing on behavioral analysis, which could be seen at the Gecko conference last week. And in our terms, we have done some research on classification approaches, providing criteria for a conceptual analysis, and we determined a study design for the empirical analysis. And our next steps will be to incorporate meta-heuristics into a unified framework and conceptually analyze them according to criteria which we will extend. And then we will perform a large amount of empirical studies and for existing approaches to determine their performance and their behavior. And we will try to focus on new operator combinations to see if we can gain additional knowledge by analyzing different operators that are successful on their own and might provide an additional benefit, or maybe are worse than if used individually. So, and then of course we will present our results in some meaningful way. And yeah, that's it. I'm open for questions now. And please excuse my voice at the moment.
No worries at all. Thank you very much for this talk. Great. So I see one raised hand by Chris.
Hi, I have a question and a comment. This is really, really important analysis. The question in part is, can this analysis keep track with the proliferation of new meta-heuristics? You actually mentioned that in your talk, that there were so many that it was very hard to do. But I think it's still important to do that.
Well, I think it will take a lot of time to include all that are out there right now.
Yes.
And then to keep track with new approaches shouldn't be that hard, because there will be much overlap.
Yes.
There will be really much overlap in terms of operators and strategies and everything. So
go ahead.
Yeah, but getting there, that we have a large set of different operators from many existing meta-heuristics is difficult. But of course, there are other researchers working on things like that. And there is a framework at the moment which has a really large operator database right now. So for one person alone, it would be infeasible, but as there's of course a community behind this idea, it should work.
Yes. The actual technical question is, the set of operators and components defines a space of possibilities. How thin is the set of meta-heuristics in that space? Because there's a bunch of opportunities there for inventing any number of new meta-heuristics that are really not much different from the others.
Well, of course, there are combinations that have not been tested yet, and I think that are a lot, but it also depends on the components and on the amount of variation within the operators.
Yes.
Because for a typical genetic algorithm mutation, if you slightly change the standard deviation of a Gaussian mutation operator, does this really count as an additional strategy? I think it's quite difficult to get to do any predictions on. on what can happen with new combinations.
Yeah, that's always one of the hard parts when you try to abstract a large collection of, well, I'll say random, but they aren't quite random, a large collection of uncontrolled elements. It's a very difficult problem. More power to you.
There's another question in the chat, and by Susan, and she asks, is there also an effort in classifying the search spaces so can match operators to problems?
Yes, there's the whole topic of fitness landscape analysis, which gathers different criteria of fitness landscapes and thus provides characteristics for the search spaces of the problems. And there are even some automated tools that analyze your problem's search space. So I think at least so. It's but it's still also ongoing research. It's not finished yet, or we do not have a consistent set of problem characteristics.
Is there another question? So at least maybe I have one. Also in Philippa's talk, we talked about the standards for the empirical analysis of these meta-heuristic components, and this finding standards maybe, or at least give guidelines and advice for doing empirical analysis on your meta-heuristic components also part of your framework?
Of course, the framework will be standardized according,
Yes.
but according to those criteria that are out there. And it will definitely be updated if the common criteria on how to evaluate your algorithms change. But I do not yet know if I would, or I do not aim at advancing any kind of standardization procedures or something like that.
Okay.
So
and
I
maybe,
will.
Sorry,
Yeah.
sorry,
No,
didn't
not
want to interrupt you. Okay, maybe a follow-up question, which steers in the same direction. Do you also plan or striving for feeding back your work into then an automated algorithm selection process? So we have this hypeuristics and also automated algorithm design or selection and configuration, and your framework might provide very, very valuable insights for how to select the most appropriate algorithm then. Do you plan this also in your research agenda?
Of course, at some point, possibly yes, but I think at the moment I have lots to do with just getting enough operators and doing the analysis itself. And
Absolutely.
it still has to be seen if these behavioral factors are really important for the selection process.
Okay. Thank you very much. If I have a look at the clock, we'll see that it's 1 minute before 12. And this means that we are now at our lunch break time. I would ask you to please be back in a half an hour so that we can continue our great workshop and all the discussions around them. And yeah, that's all I want to say so far. Thanks again for all the speakers, and especially also for our last speaker, Helena. Thank you very much again. And then we'll see us again in 30 minutes.